Yeah, so that's what we are at the last slide. So that's what we were discussing in the last day, like how do we really characterize these potential energy surfaces, and if we go along this, like this is actually reactance, this place, so that is A plus BC. So the way we should look at is that, like BC distance is this one, right? So therefore, let's say B is sitting here, right? C is coming closer to this, and A is still infinitely separated, so that is A plus. Right? So when this is coming here, so you are going to get equilibrium distance for BC, right? And that is the point here in the surface. That is the bottom of the bottom of the this diatomic curve, right? Now these are basically reactants, right? So that is R. Now when you go to this side of this surface, so those are basically products, right? So I have just flipped it around just to match with this. Now in this case, you have AB plus C, so that means C is infinitely separated, right? And let's say AB, so that means A is here, B is coming in this direction, something like that, plus you are going to have C here, right? So that is diatom AB here, that is the equilibrium distance of AB, and that is this point. Now of course in middle you are going to have all are infinitely separated, right? So when you come this point, so that is this one, this plateau, if you look at here, this plateau is the potential energy, where as geometric connected corresponds to like A plus B plus C, which that means all the three atoms are infinitely separated, right? Now then we asked that if we go from reactants to products like this, we travel in this potential surface, and then we end up here, right, this side, we come out this side, right? So in principle, something like we go from, this is the, so this is the these are the reactants, these are the products, and then we travel along the path. So what happened in between when this, like A, B and C are in a close proximity? So something like this, right? Then what is going to be the potential, what is it going to look like? Now once you realize that, and this is kind of a reaction profile, if you look at energy profile diagram for a transition state theory, right? So it's something like that. So right, so that is the, if you look at this picture, that is this is potential energy. Now reactants and products are at the same level, because I have taken the I am considering the thermoneutral reaction. Now when you go from the reactants to the products, we go slowly climb up, and then we reaches the maximum. We reach the maximum here, and then we are at the product value. So these are basically reactants value, this is the products value, and we connect through the reaction coordinates. So that means we, the A plus BC, so that means A is coming closer to B, and BC bond is getting broken. So that is the reaction coordinate we can think about. Now this transition state theory, if you look at, this is how this is connected to this potential energy surface, right? So that's what I try to connect it. Now this was the potential energy surface what you have seen. Now when you are here, right, so you are at this point. Okay, now this is nothing but the slices of this inner part of this potential oil, right? So and this is the react products, this place, and you are going to go there, that is the product. So this is R stands for reactants and P stands for the product. So and here the reactants in this place and the products are going to be there. Now when you go move along this path, we are basically going like this, right? So this is the uphill, and then slowly reaches a maximum, right? That is the middle of this. That means AB bond is being formed and BC bond is being broken, right? That is the kind of transition state we are going to look at here, this one, right? So all atoms are pretty close, and then slowly you are climbing down to the other side of the hill, so that is going to go to the product, right? So that means when you go along the reaction path like this, so you are basically going in this path, so you are passing through a maximum, like here it is in a transition state theory. If you look at here, that is the way we draw it, that is the maximum, and you go to the product, right? Now what is the feature of this point is that, now if you look at, if I go perpendicular direction, now I was moving like along the reaction coordinate. Now if I go perpendicular direction, so that means start from here going down along the valley and going down to the well and then climbing up, so that is the path you can think about. So this is the reaction coordinate, and this path is I am showing is perpendicular to that, right? Now if you take perpendicular direction, so that means I am at this point, so that is the plateau. So that is let's say start kind of here, right? Now when I'm going down along this in the perpendicular direction, so I'm moving along this direction, right? So that means I'm following kind of path like this. So at this point, then I'm slowly climbing down, and then I reaches the bottom here, and other side again if I go, this is going to go up, right? So that is the point when you are here, right? So I'm climbing up at the bottom to up, so that is the point. So let me just make a cross here, and that is the point we are going to be somewhere here, right? We're starting here. So now what is the special feature of this is that, now if you look at this, when you go along the reaction path, which is basically nothing but the minimum energy path along this, because if you go away from this path, either this side or this side, you are going to go in higher energy, right? So it is true for every point on this. Now when you are going along this reaction path, minimum energy path, you reaches a maximum, right, and go to the other side of the valley, so that is the product. Now again this point, when you travel perpendicular direction along this, right, then this point is going to be minimum, right? So along the reaction coordinates, this is maximum, but perpendicular to the reaction coordinates, this is going to be minimum, right? So this is kind of, so at this point you can think about like maximum and minimum two condition has to be satisfied. So that means the point, this is a features of the point where it's basically called the saddle point, because it looks like a saddle. I'll tell you what is the saddle. Like if you have seen the horse riding, where you the horse rider sits, okay? So let's say we are sitting on the back of the horse, and normally you sit on a what is wooden made uh, sitting arrangement, right? So that is basically, one side. This is if you are going from, let's say this is your right leg, this is your left leg, then when you go for, yeah, tell me. Yeah, so what I was telling is that, like, if we go from so this is looking like a saddle. If you have seen the horse riding, that's what I was discussing. So let's say you are sitting on the back of the horse, and the platform where you sit, that is wooden made stuff, and there, if you are having, let's say you are sitting, this is your left leg, and this is your right leg, you are sitting, and your front is that side, right? Then when you go from your left leg to right leg, you are going through a maximum, right? But exactly perpendicular direction, if you think about, then this point is going to be minimum. So here maximum in one direction, and exactly in perpendicular direction we are going to have minimum, right? So therefore what you get, this is it's called the saddle point, this point at which both maximum along the reaction path and minimum along the perpendicular direction meet. So that is the saddle point we say, and these points around this uh, saddle point are nothing but the geometry around the transition state, right? So that is the correlation is between, like, this region, if you think about, that is connected to this one, right? So that's what we are going to connect it. So that is the feature what I wanted to discuss, and now this is for the reactants going through the production transition theory, and you are going through a maximum, and this transition state point, the geometries are basically geometries around the saddle points. That's what we're going to get, right? Now this is a thermoneutral reaction what we discussed. If you go for the let's say exothermic reaction, then or the endothermic reaction, we are going to get like this saddle point will be either on the reactant side, or it is going to go to the product side. So that's what we are going to look at, right? Okay. Now before getting into that, what I prefer is that to discuss the contour of how do we really use the contour plot to characterize the potential energy surface, right? So